This is video 26. In this new part, we introduce visible tiles. They are the key tool to go through microscopic reasoning. In this video, we give some definitions and basic properties. We start with some basic definitions. Consider a simple finite path assembly P producible by a deterministic tile assembly system. The seed is in black. For the moment, we only consider the path assembly P. We say that a tile is visible from the west in P if and only if there are no other tile of P which is west of this tile. For example, the tile P7 is visible from the west. The ray which starts in P7 and goes to the west is hatched. This ray does not intersect with the path assembly except in P7. Here, the tile of the path assembly P which are visible from the west are drawn in gray. We denote by VP the set of the indices of the tiles visible from the west of the path assembly P. We will mainly work with visibility from the west, but sometimes we will need visibility from other directions. For example, the last tile of the path assembly P is visible from the east. The ray which starts in this tile and goes to the east is hatched. This ray does not intersect with the path assembly except with its last tile. Also, note that this ray does not intersect with the seed. A tile visible from the west is hidden by the seed if and only if this tile is visible from the west and if there exists a tile of the seed west of its position. For example, the tile P1 and the tile P21 are hidden by the seed. We denote the set of the indices of the tiles of the path assembly P hidden by the seed by HP. Here are some quick remarks. Consider an ordinate y which is between the minimum ordinate of P and the maximum ordinate of P. Then the path assembly P has exactly one tile visible from the west of ordinate y. As a corollary of this remark, the number of tiles hidden by the seed is trivially bounded by the size of the seed. These remarks provide a bound on the number of tiles visible from the west and not hidden by the seed. Tiles visible from the west are useful to study local constraints. Consider a tile of a path assembly P which is never the first nor the last tile of the path assembly. Let I1 be its index. We will enumerate all the possible neighborhoods of this tile. Here we have drawn one possible neighborhood. The tile Pi1 is in the center of this figure and has two neighbors. The next tile which is Pi1 plus 1 and the previous tile which is Pi1 minus 1. The direction of the path assembly is given by an arrow. Here are all the different possible neighborhoods of the tile Pi1. There are 12 of them. Now if the next tile is north of the tile Pi1 then we say that Pi1 exits to the north. If the next tile is east of the tile Pi1 then we say that Pi1 exits to the east. If the next tile is west of the tile Pi1 then we say that Pi1 exits to the west. If the next tile is south of the tile Pi1 then we say that Pi1 exits to the south. We say that the tile Pi1 is directed to the north if and only if either this tile exits to the north or if the previous tile is south of this tile. 5 of the possible neighborhoods are directed to the north. We say that the tile Pi1 is directed to the south if and only if either this tile exits to the south or if the previous tile is north of this tile. 5 of the possible neighborhoods are directed to the south. Note that a tile cannot be directed to the north and directed to the south at the same time. Also, there are 2 neighborhoods where the tile is neither directed to the north or to the south. Now consider that the tile Pi1 is visible from the west. Then in 6 neighborhoods, a tile is west of the tile Pi1. We have to remove them. Only 6 neighborhoods are left. 3 of them are directed to the north and 3 of them are directed to south. Thus a tile visible from the west which is neither the first nor the last tile of a path assembly is always directed to the north or directed to the south. Tiles visible from the west are a powerful tools to find some global constraints on a path assembly. We present here some of these global constraints. We say that a segment of a path assembly P is visible from the west if and only if both of its extremities are visible from the west. Similar definitions are used for exiting to west, north, south or east and directed to the north or directed to the south, we say that a candidate segment of a path assembly P is visible if and only if it is visible from the west, directed to the north and exists to the north or to the south. Visible candidate segment will be very important in the following videos. In our example, the tile visible from the west are drawn in gray. In this example, we consider the segment of the path assembly between index 7 and index 45. This segment is visible from the west but it has no other properties. If a segment is visible from the west, then we can use these visibilities to create a simple B-infinite path. This path can be used as a window W. In our example, this window is in gray. We consider that the position W0 is occupied by the tile P7 and the position W38 is occupied by the tile P45. This window creates a cut of the grid G1 and G2. We remind that the graph G1 is the left side of the window W. In our example, this graph is hatched. Remark that the ordinate of the tile P45 is strictly greater than the ordinate of the tile P7. In this case, any tile visible from the west whose ordinate is between the ordinate of P7 and the ordinate of P45 belongs to the graph G1. Also, if the index of this tile visible from the west is lower than 7 or higher than 45, then it cannot be visible from the east. For example, the tile P1 is visible from the west and belong to the graph G1, then it cannot belong to the window W and thus it is not visible from the east. We now introduce exposed path assemblies. Until the end of these videos, we will almost always consider exposed path assemblies. Consider a finite and simple path assembly P. Moreover, we suppose that the first tile of this path assembly is the only tile of the path assembly which belongs to the seed. We assume that the maximum ordinate of this path assembly is strictly greater than the maximum ordinate of the seed. The first highest tile of a path assembly is the first tile of this path assembly of maximum ordinate. We denote by T the index of this tile. The till of the path assembly P is the segment of P from index T plus 1 to its last tile. In our example, the tiles of this segment are hatched. The till of the path assembly P is short if the minimum ordinate of the tail is greater than the minimum ordinate of the segment of P from its first position to the index T or the minimum ordinate of the seed. In other words, the tail does not go below the seed or the segment of P from its first tile to index T. Otherwise, we say that the tail of P is long. Finally, we can end the definition of an exposed path assembly. To the three previous conditions, we add the three following ones. The tile PT exits to the east, the till of the path assembly P is short, and the last tile of the path assembly P is visible from the east, and this visibility is not hidden by the seed. The example is an exposed path assembly. Note that if the tile PT is the last tile of the path assembly, then we consider that this tile exits to the east. We end by defining our last special tile of the path assembly P. The first lowest tile of an exposed path assembly P is the first tile of minimum ordinate in the segment of P from its first position to the index T. We denote by B the index of this tile. By definition, B is always strictly less than T.